Hello, for today's video lecture we're going to be talking about calculating the center of mass via the first moment integral. So the center of mass of a body is going to be the center point of that body when we average everything by mass. So one of the important things is gravity forces are going to exert zero net moment about this point in every direction. So if I imagine a body, some miscellaneous body, holding it by the center of mass, gravity is a distributed force, which means it's pulling down on every little piece of that body. Each of those pieces, each of those forces on the pieces is going to be exerting a moment about the center point. So at the center of mass, all of those moments are going to cancel out. So the gravity forces on the right and the gravity forces on the left are going to cancel each other out. So this is why it's kind of essential to know the center of mass for mechanics problems, because rather than modeling all of these gravity forces as a distributed force, we're usually going to model the gravity forces as a single point force. So there's no moment. We need to have this single point force act at the center of mass. And so this is why we need to know that point. Alright, so for a part with a uniform density, anything made of kind of a single material, the center of mass is going to be the same point as the centroid. So we can use those two interchangeably. When we have non-uniform density, so we've got a piece made of more than one material, or a piece that has kind of a continuously varying density, then we need to do those center of mass calculations. Alright, so to find the center of mass for a 3D shape with integration, we want to use the 3D first rectangular mass moment integral. So this is the kind of type of integral we need to use. And since the centroid is a point which has an x, y, and a z coordinates, we're going to need to do potentially up to 3 calculations. So one for the x, one for the y, and one for the z. Which means we're going to be doing a lot of calculus for this. Alright, so finding the center of mass, we're going to look at kind of where this comes from. So to find the average x-coordinate of a set number of points when averaged by mass, we would add up the masses times the x-coordinates. So the mass at each point times the x-coordinate of that point, add all those up, divide by the total mass, and I would get the average x-coordinate. Alright, so to find the average x-coordinate of an infinite number of points in a volume, when we were going to integrate kind of the same function. So integrating from some minimum x value to some maximum, I'm going to multiply the density times that kind of very small volume. That would give me my mass. And I'm going to multiply that by the x-coordinate at each point. So as I move from x minimum up to x maximum, I need to write out the density times the rate of change of volume times the x-coordinate, and again divide that by the total mass of my piece. Alright, so let's talk more about some of these things. So if we substitute in the volume times the density for the mass, we get the following. So this is the mass in the bottom. It's density times volume. If I have a uniform density, I can kind of pull that density out of the integral on the top, and this density here and the density here cancel each other out, and I'm left with what is basically the centroid calculation. So this is why for uniform density parts, the centroid and the center of mass are the same thing. I only need to worry about kind of keeping this density term in there if I can't pull this out of my integral. Alright, so let's talk about what some of these terms mean for our calculation. So here I've got a cone. It's got a kind of lower density on the bottom, higher density up on the top. So density is changing, and as I go, I'm looking for a z bar, so the average, kind of the center of mass in the z direction. So if I want to find the position of the center of mass in the z direction, I want to go from some minimum z value, so whatever the bottom of the shape is, up to the top of the shape. That's going to get multiplied by the equation describing the density at any x, y, or z position. So I need to figure out, the density at z minimum is such and such, the density at the top is such and such, and I've got kind of a linear relationship between the two. So I'd write out the equation describing the density at any value of z. I'd multiply that by the equation describing the cross-sectional area at any given value of z. So as I move from the bottom up to the top, the cross-sectional area is always going to be a circle, but it's going to get smaller and smaller. And so I need to find an equation describing that area for any value of z. So I'm multiplying the density function times the dv function. I multiply that whole thing by z, and I'm going to divide this moment integral, after I evaluate that, by the total mass of the object at the bottom here. Alright, so with that, that's all I have for the center of mass calculations. Thank you for watching and hope to see you again.